Okay, well, with that, let's give Nick a virtual clap or turn on
Thank you.
microphones and actually clap out loud. And okay, Nick, you can now turn into a participant like
Thank
magic.
you.
And we will move on to our next event. Thank you so much. It was really cool.
Thank you for listening.
You're welcome. All right. Turning this over to Sean. Take it away, Sean.
Okay, let's see. Do we have got 27 participants? So yeah. So today's workshop is going to be about data movement. There's 3 of us. We're going to be giving the presentations and walking through some of the exercises we're going to cover today. So Alan Winnery, he is the University of Hawaii Systems Chief Internet Engineer, and he has over 30 years of experience doing what he is going to talk about today with data movement and figuring out challenges with getting data moved around the globe. And then we have Luke Nelson. He is one of our Hawaii Data Science Institute fellows. So he's going to be doing a good amount of presentation covering doing some data transfer with Globus and rclone. And then my name's Sean Cleveland. I'm a cyber infrastructure research scientist. So I'm kind of doing the introduction here, and I will briefly talk a little bit about some other methods that we've got here. So, so this workshop today, hopefully, will introduce everyone to some of the challenges involved with data movement, and maybe some challenges you've already experienced, maybe some methods that you might pursue to figure out, where maybe bottlenecks in your data transfers could be happening, as well as some of the tools that you can use to move some of the larger data that you may have to shift around to gain access to or give to collaborators as you're doing your research. So the prerequisites for today, we will do some stuff that is going to require some basic SSH and command line tools, specifically for some of our rclone. You will need an account with Mana today to be able to use the Globus account stuff that we're going to set up, as well as rclone. And then if you want to use some of the Globus features, or you want to use Mana, you will need a modern web browser. So just looking at some of the setup here for the workshop, if you do want to access the Mana Open On Demand web interface, if you go to, actually I should have done this initially. Let me give you everyone the materials. So here is a link to the materials that we're looking at here. So that link should take you to this homepage here. And if you scroll down here to the schedule and you click on setup, this will take you to this area where I just talk about prerequisites, but there's a link to mana.its.hawaii.edu, and this just will take you to be able to log in with your UH credentials to the Mana Open On Demand web interface. We do the dual factor. So yeah, once you're there, if you see this interface, there's a clusters tab here, and you can access a shell just by clicking that, and then you'll have an SSH terminal shell that you can use if you don't have one on your own machine. Other things, any files that we'll require for this workshop, we will download as we go through the tutorial, so nothing to grab ahead of time. If you'd like to give feedback during the workshop, there is a way to access the reactions in the Zoom tools. So at the bottom of your screen, you should see something like this that looks like a little reactions button. And if you click it, there's a way to hit a checkbox and say, everyone give us a green check if you're okay, or a red circle with an X in it if you're having problems, or raising your hand if you have a question. You can also just speak out during the workshop. If you don't see this reactions here, you might need to click the more button and click the reactions to get to that interface. So with that, I think we will head towards the introduction to scientific data networks, and I will just stop sharing and hand it over to Alan. He's going to be doing some presentation via some slides here. but we can follow along with the materials if you care to. So Alan, I'll hand it off to you.
Unmute. Hey, I found an unmute button. It doesn't always happen. Okay, so that's my title slide. Most important is my email address, because as I'm going to tell you next, these are your takeaways, even if you ignore every other slide in this presentation. First of all, many people, among them Sean and I and Gwen and some other people, we're employed specifically. We're actually paid to answer your questions and help you move data effectively. And not only that, we kind of like doing it. So when we get your email or something about you've got a data transfer that's not performing well, or you just like to know whether it's performing well, it's actually kind of interesting and satisfying for us to work on those things. If you'd stopped me in the street a month ago and asked me how much speed should I get for my data transfer, I would have said, well, it depends, you know, and nobody likes that conversational impasse where the person's considering all these possibilities. Well, I'll just throw down the gauntlet and say you should expect hundreds of megabits per second of file transfer speed on a usual transfer between UH and other academic and research endpoints. If you're not getting that, you should ask us why not. If you are getting that and you want more, you should ask us how. Just remember that making data transfers perform well can be somewhat deep and complicated, but it's not mysterious. There's a limited depth to it, and we will find a way. And it's almost never about getting some fiber fixed under the ocean or something. It's usually more tractable than that. So some of these topics are going to seem maybe a little odd. And this is kind of like excerpts from the 1-week web workshop that I'm probably never going to deliver, and you would probably never want to sit through, but I'm trying to hit some points that will help dispel some of the fuzziness that people have about what your place in the internet is and how your stuff goes to other places in the internet. And you need to know that pretty much all retail marketing is gibberish. I found this Ethernet cable on the hook at Target, and there are several contradictions and nonsensical statements on this card. And you can look at that slide later, but it's just an example. This is also true when you go to look at an internet service provider's plans that you can buy, how much speed you're going to get. A lot of it will just simply not make sense. And the reason is probably that the people who understand the thing at that company are not the people who write the copy for the package or the website. So you just need to know that if you're getting your information from Ethernet cable packages, you're probably out to sea a little bit. This is probably a good quality cable. It's at a good price. I would buy one and use it, but don't read too much into the packaging. So we're going to talk for a few slides just about how everything connects together. For the most part, interfacility, intercity, international links are glass optical fiber. These are this picture has 4 different levels of cladding and armoring on optical fiber. This is submarine fiber. It's a stub of fiber that's situated onto a base and sticking straight up. So the one on the left, the white cladding on the outside, is about the same size as my thumb. And so the one on the left is the deep water fiber cable, which means and when it's laying under 1,000 feet of seawater in the middle of the ocean, there really isn't much that's going to happen to it that might hurt it. The armored stuff is for coming ashore on a continent or on an island. And as you can see, there are different levels of armoring and cladding. The other thing you need to know about this slide is that residential stuff, the stuff coming into your house, includes fiber to the curb. So that's also fiber, very similar fiber, but it's also, there is also cable TV, internet over cable TV, also called DOCSIS, and there's probably still some DSL in the world out there. As you go on, mostly servers and data centers are mostly interconnected by copper, although there is some fiber. If the server has a 10 gigabit interface, it's kind of you flip a coin. It might be fiber, it might be copper. Of course, campuses and residences, as you would guess, because you experienced it directly, they have copper and Wi-Fi. Mobile is, of course, big. There's LTE, 4G, 5G, further Gs. Satellite, which enjoys this interesting mythology in the scripts of movies. There's always a Jeff Goldblum character who's trying to do something to satellites to affect cell telephone service, and it just doesn't work that way. Satellite is actually very limited on continents, although people have DirecTV, Dish Network, internet that they get. VSAT, very small aperture terminal satellite stuff, is still a very major influence in the Pacific because there are a lot of places. There are like 100 populated places on Pacific Islands where they don't have any fiber. O3B is a satellite brand that was set up in order to serve the other 3 billion, and it's satellite for underserved populations. And of course, the game is about to change because Starlink they've shipped 100,000 Earth stations. They are the first satellite provider that has their own internal launch capability. You think about how that changes the picture. Expect Starlink to have an influence going forward. Long distance cables, if you see a reference to a long distance cables between points, they often isn't really the word. They always have more than one logical link. Sometimes that's due on a single fiber. They have different colors of lasers that operate together in the same glass, and that's called wavelength division multiplexing. You'll also see different virtual LANs operating the same Ethernet trunk, which is referred to as VLANs. These are all Googleable terms for you to check back later. You also need to understand that there are the several internets, the differences between different flavors of internet. So commodity, what we refer to as commodity internet, is the everything else. It's the commercial internet, the residential internet, the things not reached by research and education networks. And if you call the commodity, the help desk at a commodity provider, it's probably a little hit and miss as whether they can help you with a data transfer problem. Not because they're less capable, because they face a different set of requirements and requests from a different population. And so RENs, or research and education networks, are special networks which interconnect research and ed community resources together. They have research and academic friendly support staff. Many of them have people like Gwen and Sean and I, whose purpose in life is to help you get your transfer going. Regional RENs connect to national RENs connect to each other, and RENs tend to focus more on performance. Exchanges are places where different networks within a region can interconnect so that the traffic doesn't take the long way around, or organizations in a region with similar needs will interact together. There are different flavors of RENs or of exchanges. You know, there could be REN commodity or both. There's also this phenomenon of CDNs, content distribution networks, and caches. So if you ask for a movie from Netflix, you will get it from the nearest Netflix cache, which is probably in, I'm guessing it's in Mililani, if you're on Spectrum. It may be elsewhere if you're on Hawaiian Telcom. It might be in Mililani on Spectrum if you're on Hawaiian Telcom, because we have exchanges for traffic to stay local in Hawaii. Also, if you download Microsoft or Apple updates, if you download YouTube videos, they're on Google Global Cache down in Mapunapuna at the DR Fortress. So just to let you know, it's not always about a resource exists in some spot on the earth and then the internet takes you there and you get the stuff from that resource. There's a lot of energy being put into putting resources out where they can be reached quickly. So to choose between these flavors of internet, you don't have to do anything. If you go from university to university, the traffic will travel over REN links. You go from here to NCAR, the National Center for Atmospheric Research in Colorado. It will travel over REN lengths, or it should, and that's something you can call us about if you're traveling over a commodity path to a research or education resource. You should give us a call. So a little bit about University of Hawaii System's place in the world and the internet. There are 10 instructional campuses and about 40 other facilities across the 6 public populated islands in the state of Hawaii. Commodity connections for regular internet, we have 100 gigabits to SCENIC, which is the Corporation for Educational Network Initiatives in California. We have a quasi-commodity through Internet 2, which you probably heard of, I2PX, which the commodity stuff that comes through I2PX tends to be things that have been deemed beneficial to be very reachable for research and education, but they're not exactly research and education resources. And then we have, lastly, we have a 10 gigabit connection to Hurricane Electric via DR Fortress, where we can get your Yahoo and your Burger King. Research and education networks, there are maps coming, so you don't really have to get it all from the slides. You have to endure the 1,000 words to see the picture. So on Oahu, we have peerings with, or from Oahu, we have peerings with Internet 2, SCENIC on the REN side, RNet, which is the national REN of Australia, REANS, which is the national REN of New Zealand, the Western Research Network, which is on the continental US, an interconnection REN, and a link to GOREX, which is the Guam Open Research and Education Exchange in Guam. We operate GOREX, we operate the Hawaii Internet Exchange to keep local traffic local within Hawaii. And we also peer with the DR Fortress Exchange in Mapunapuna. Here's a picture which shows how UH is situated within the surrounding networks that we peer with to some extent. It's kind of called out by fiber cable name instead of by peer name. But the red stuff and the orange stuff, the red stuff is the on-island networks on each of the islands with stuff. There actually is some stuff that I would have colored red on Kauai, but it doesn't show up here. Of course, Kauai has a smaller population and fewer resources to reach. Mauna Kea, of course, is big in the astronomy biz, Big Island. Mauna Kea, which is on the Big Island of Hawaii, is big in the astronomy biz, and as is Maui with Haleakala. So the orange and the red are part of a state government consortium between University of Hawaii Department of Education, the state library system, and the DAG's central IT for the state of Hawaii. We share those resources and exchange inter-island and on-island traffic. And then the blues and greens are other things reaching other, as I said, REANS and RNet and GOREX and et cetera. So another picture, this is our place in what we call APONet, which is a consortium of networks around the Pacific Rim. And it just is a zoom out from what I've been showing you. You can see that Guam is over here on the, let me get my pointer active. Guam is right there. And there's a link from Singapore, there's a link from Tokyo, there's a link from Sydney, there's a link from Honolulu. And that shows GOREX's place in the world. Moving on to North America, we have a picture. This picture is from the Quilt website, and it's got the regional RENs in the 48 states with of course, links to Alaska and Hawaii. And this just gives you some idea that the regional RENs are, some of them are associated with a single state, some are multiple states, some of them are regional interconnections, and some of them are sweeping inter-REN connection like WRN, which is the one with the long orange arcs on the left-hand side, because there's so much space in the Western United States. And the next picture is this same picture with the Internet 2 network underlaid under the REN picture. And that shows you how Internet 2 kind of interplays with regional networks. So you can see that each of the regionals has a pairing with Internet 2, and you can see that Internet 2 has fixed points that a organization or a network needs to reach in order to peer with them. And so it's not really, Hawaii has to go to Seattle and to, well, I would say Los Angeles to peer with Internet 2. And that seems like we're getting, it's a special case for us, but it's not really, because the others have to build long links to get to their nearest Internet 2 peer point as well. So this is a picture of NOAA N-WAVE, the National Oceanographic and Atmospheric Administration. And we are not exactly part of it. We're not an N-WAVE site, but we do provide connectivity. We have an agreement with NOAA to provide connectivity for N-WAVE for their missions in Honolulu. And lastly, there's the ESNet, which is a national research network operated by the Department of Energy for DOE labs. And of course, to reach into Switzerland and France for stuff that's at CERN, including LHC, the particle accelerator. They touch in the Netherlands, Switzerland, France, and the UK, and Europe. And we actually have a couple of research activities that bring data from CERN and Switzerland to Hawaii. And those will travel on ESNet for most of their hops. And usually when they get to the West Coast of the United States, they'll hop over across Pacific Wave onto one of our links to come to Hawaii. This is a snapshot of fiber cables in the Pacific from submarinecablemap.com. It's a zoomable, clickable, slippy map that you can play with if you're interested in fiber cables and you want to see what's going on with that. This is a medium scale Juniper router, an MX480. This has connections. You can see that there are connections. These are 1 gigabit copper connections over here. There's 10 gigabit fiber connections. Down here are 200 gigabit connections. And there's empty space, so we can plug in more. But just to give you an idea of what the thing looks like, this is on the left is a fiber distribution patch center in our old data center at the Manoa campus. It just shows you fiber cables coming in. The yellow fiber cables are typically single mode fiber. The orange are multi-mode, and the blue ones are also multi-mode. On the right, there's a stack of Ethernet switches for distributing gigabit Ethernet around to other switches and to buildings and to rooms. And this is just a distribution rack with some more core switch stuff in the bottom. So if you've got a data movement task that you want to do, and you are kind of working out what kind of throughput you get between points, one of the tools you can use is iPerf3, which here's all the links to get it. You can run it on Windows, you can run it on Mac OS, you can run it on Linux, you can run it on other things. I think there's probably even an Android client for it. And then I mentioned also NUTTCP, which there was a program called TTCP, and this is the new version of it, although nobody says new TTCP, but it has a couple alternate features in it, which are kind of interesting. For instance, you can start NUTTCP on 5 different hosts, and then you can sit on a 6th host and tell it to run tests between hosts 1 and 2 and hosts 3 and 4 and hosts 5 and 1, which might be interesting or useful. This is an example of an iPerf3 test between Honolulu and Baltimore. On the left, I did iPerf3 -S, which runs a little server, and on the right, in Baltimore, I ran iPerf3 -C in the name of the machine on the left, and it sends a bunch of packets from one to the other. And If you look closely, you will see that the reports of throughput are different in the sender and the receiver, and which is kind of interesting. And of course, there's a temptation to rerun the test and make it make sense. But I really want you to see things warts and all, and see so that when it happens to you, you don't go, oh, why is my thing wrong? It's what's happening is the effects of queuing and various system resource contention, et cetera. Not to worry. So perfSONAR is another thing, requires a little more involvement to get access to. There are permanent test points at many places around the world. There's a link on the next slide. You can look up a map to see where perfSONAR servers are. perfSONAR servers run periodic tests between each other, and they record the results. They prevent test conflicts. If you ask a perfSONAR server for a throughput test, it will wait until any current throughput tests are finished before it starts another one, so there's no conflict. Very academic and research centric. There are many servers around the world, especially in REN networks. We have many servers in UHNet. We have on Guam and in Japan, and they're all across all of those networks that I showed you in the previous maps. You can install the clients on a Linux laptop. It may be possible to install the clients on a Mac OS laptop. It used to be possible, and I have not heard that it was, and perfSONAR has changed. So I won't commit to that. The perfSONAR toolkit is available as a Docker container, which will work on Linux-based Docker engines. Getting the networking side working on a Mac OS or Windows Docker desktop is complicated, and if possible. So if you really have a weekend with nothing to do, you can look into that. Maybe I will too. Some links for perfSONAR meant to be visited later. Something that's super easy to set up and will give you some facility into checking whether or not a path is working well for you is this LibreSpeedTest, which has a GitHub repository there in the link at the top. You take this code, you drop it in a directory on any web server. It will provide browser-based throughput estimate for a path. There's also a command line client. I have one in my house, which is good. If something's slow, I can check first of all to see if my home network is working well. For some reason, I'm in charge of admitting people. And there is one at the Manoa campus, and of course, I'm kind of posting a link in front of a bunch of people. I don't know what's going to happen when you all hit it, but have at it. You can't hurt it. It may just operate. It may just work slowly. Sometimes it reports more than possible throughput on a 1 gig E. Sometimes you'll see 1.01 gig, which is it's a cheap little JavaScript thing. Give it a break. This is on my home network from my laptop across a gigabit Ethernet to the home router. It gets right up there, almost a gigabit throughput, which is 990 and 982 are typically what you see when a gigabit is maxed out. There's also LibreSpeedTest, and I want to mention this because it's useful. I also want to mention it because it may not be exactly what you're looking for. So if you load speedtest.net, you will see a speed test page, and there'll be a big go button. And if you touch the go button, it'll test from where you are currently sitting to nearby servers in Hawaii, unless you're sitting somewhere else, and then it'll test to those servers. And it will also, in Hawaii especially, the one like the Hawaiian Telecom server and the Spectrum server will work together to fill your link. So it's about how much bits your link can eat, and less about your transfer speed from a given server to your given computer. You can also choose change server on the landing page, and then you can go anywhere in the world. I've had tests to Lagos, Nigeria, and to Majuro in the Marshall Islands. It's kind of a fun way to poke around the worldwide internet and see what happens, depending on what your definition of fun is. So I'm going to talk a little bit about how computers and networks are really put together, and I want to define what queues are, just in case you're not up on that. So queues, also known as buffers, there's not a real distinction. I'm speaking generally about buffers and queues, and for the most part, I'm speaking about what we call FIFOs, first in, first out queues. And queues are places where things arrive to wait for something, like the line at an ATM machine. Data waits in queues for a chance to be transmitted further. Queues are the reason everything in the universe is not stuck waiting for everything else. And that sounds like a joke, but asynchrony is what lets the world continue to move. Asynchrony being what's provided by queues. The ability to reach a point and then wait for something else to happen before you continue. So this is a common mental picture. People want to transfer bytes from one side to another, or from one place to another, and they think, here's my computer, here's the network. If my performance is not very good, then it's probably the network, because my computer is a black box, and I never had any problem until I plugged my cable into this network, right? So, but you need to understand that the network starts several boxes into your computer, into several stages into your computer. So when I ran that iPerf test, the iPerf program invents packets out of thin air. It writes them into a buffer in RAM, and then for TCP, which is part of the operating system, part of the kernel, for TCP to grab, and then TCP hands it to IP, and IP hands it to Ethernet, and then it goes on the cable out of your computer and it hops across the net. And all of those green boxes have very similar blue boxes inside them along the way. And then it gets to the other side, and TCP writes it into a buffer in RAM to hand to the iPerf server on the server side, and the iPerf server validates that it got the packet and how fast it got it, and then it does away with it, deletes it. So this test tests the network that's in your computer out onto the cable, across the internet, up the cable, and back into the other computer, and reads and writes things from RAM. Now, reading and writing from RAM is very fast. So this speed will probably be limited by what we're calling the network. If you go to a file transfer, you start with a file. The file hands stuff into block IO, which leads from your disk system or from your storage system, whether it's an SSD or a spinning disk, and into several more layers. If you were being really detailed, there'd be like 5 or 6 layers instead of 2 yellow layers. And then it hands it into that buffer for TCP, and away we go. When it gets to the other side, it's got to go back through that chain and up and writes it to the file. Now, storage systems, even SSDs, which are much faster than spinning drives typically, are quite a bit slower than RAM. So when you try that iPerf transfer, RAM to RAM will be very fast. When you try the file to file, disk to disk transfer, you're going to be working with storage systems, which are slower. So you're going to get less throughput. All right. So this is a picture which shows, again, a simplification of every place that there's a queue or buffer along the way. There's probably more than this, but you can see that the whole mess is just processes taking bytes and putting them into buffers so that other processes can take them out of buffers and move them along their way. So notable points: data moves by processes, either in queuing data or dequeuing data. Some network queues have easy adjustments because the large variation in latency on networks, and optimizations vary by use case. Storage systems, on the other hand, mostly benefit from design choices, meaning when you build your storage system, you choose to have dual SAS controllers and 16 terabyte, 10 terabyte drives in parallel instead of a single drive in a laptop. and you get more throughput into that storage, into and out of that storage system. Most of the defaults and things like Linux and Windows and Mac OS and et cetera support many users sharing a resource. If you look at the way Linux is designed, it supports many people taking many files from many places in the storage system at once. But our use case, when we build such things as DTN, such things as Mana and company, is to commit entire machines to a single purpose. So sometimes there are optimizations to be had that are counter to the default design of the systems. So I'm going to talk a little bit about why TCP acts as it does, and just in case you don't know what TCP is, pretty much everybody has heard that term by now, either in the term TCP/IP or somewhere else. It's a transfer control protocol. It was designed in 1970. It's a protocol which carries almost all internet data. Understanding TCP configuration can be the key to faster data transfers, especially if you want to do a lot over a long path with a single stream. TCP is being displaced to some extent by a UDP-based protocol called QUIC. Originally started at Google. It's in the IETF as being codified and standardized in the IETF. It really has not had much effect at this point on research and academic data transfer, although it may very well emerge soon. And you may start to see quick transfers. The useful thing about developing a UDP-based transfer protocol is that TCP is built into the kernel of operating systems, and it's more of a, it's got more mass. It's harder to change it. It's kind of like a constitutional amendment. Building your own protocol, and actually there have been various cases of Google, Facebook, others rebuilding network protocols to suit their own purposes instead of relying on the underpinning protocols. So we'll do a little bit of a thought experiment here. If, let's say the packet takes 10 milliseconds to travel from sender to receiver, which is approximately the real world time for a packet to travel from Los Angeles to San Diego. And that's the little red packet. It's transferring across a 10 millisecond path. An acknowledgement for receiver to sender would take 10 milliseconds to return to the sender. If we wait for an acknowledgement for each packet before sending another, then we can only deliver one packet every 20 milliseconds. So if we go packet, wait for the acknowledgement, packet, wait for the acknowledgement, packet, wait for the acknowledgement. The packets have a maximum size in most cases of about 1,500 bytes. So this limits the throughput on this path to 0.6 megabits per second. So, and that's probably not what you were looking for in terms of throughput. So if you establish a rule that 10 packets can be sent before any acknowledgement is received by the sender, then 15,000 bytes can be sent every 20 milliseconds or 6 megabits per second, which is better. The number of unacknowledged packets is called a TCP receive window, which can be affected by user settings in most computer operating systems. So when the window size equals the maximum amount of data that can be sent by the sender's interface during the 20 milliseconds. Okay, so when you have sent so many packets that you're still sending the last one when the acknowledgement comes back, then there's no point in, you cannot gain further throughput gains by increasing your window. There's no benefit to increasing your window. Increasing your window, you could increase your window, but you would just make yourself more vulnerable to loss. If because the bigger the window, the more vulnerable you are to a packet being lost. If the sender has a 1 gigabit interface, and then each 1,500 byte packet takes 12.4 microseconds to transmit, meaning that TCP window of about 1,612 packets reaches maximum TCP throughput approaching 1 gigabit per second. In practice, the window size is expressed in bytes, as in 2.4 megabytes. Using the bandwidth delay product equation we're about to mention, it is estimated at about 2.5 megabytes. So it's all estimate is a really good word to point out there. So modern operating systems Linux, BSD, Windows, Mac OS, Android, iOS should perform pretty well on paths less than about 50 milliseconds round trip time. The closest points in the US mainland are about 45 to 50 milliseconds away from Hawaii. What's generally adjustable in operating systems is to limit how large a window can grow. So when you, as in the default configuration, most operating systems, including Linux, are set up such that if you wanted to do Hawaii to Baltimore, 120 millisecond path, you would need to open up the window to get a maximum window active to fill that entire path while you were transmitting data. The bandwidth delay product, there is a Wikipedia page by that name. TCP receive window in byte is round trip time in seconds by the effective byte per second rate. The maximum TCP receive window is 2 gigabytes, which means that the max round trip time that can support 100 gigabit per second transfer is 171.8 milliseconds. That's notable because with 10 megabit, there are 10 gigabits or 40 gigabits, it really wasn't an issue because there aren't any paths that are 10 times that, which is 1.7 seconds, or if there are, they have serious problems. And so if you wanted to go further, you'd need more than max window. But of course, you don't care because going 100 gigabits is quite an accomplishment, even if everything goes in your favor in a single stream. Most modern OS is auto-tune. Default limits are insufficient to moving data. I already said that. And there's a fasterdata.es.net site, which is a kind of a home to a lot of information like this about how to tune your computer, how to get your data stuff to transfer better, how to build your storage systems, which is provided by the Department of Energy. Another element in data transferring is bursting. And so if you show the packets as evenly spaced, as I did a minute ago, the actions of machines made of processes and queues tends to make the transfers bursty, and meaning that 100 megabit per second transfer across a 1 gigabit per second path is often really more like small bursts of 1 gigabit per second packet trains with long gaps between them. And so if two of these bursts arrive at the same queue in the same time, because there are multiple stations, multiple senders sending through the internet, if two bursts from two different sources arrive at the queue at the same time, it'll overflow the queue. But if you space the packets out, you can inject more space in there and the queue will do better. And this is typically done in practice with a feature in Linux called fair queuing. There's a URL to a site that addresses how to do it in Mac OS. This is an example of 4 parallel streams from Honolulu to Baltimore. Note that on the left, you've got transfer rates up into the thousands of megabits per second, but it's all bumpy and not smooth. And on the right, you've got a retransmission graph that's scaled to 16,000 retransmissions per second. But here we are, and we paste each of the 4 streams to 3 gigabits per stream across that same path between those same 2 machines using the same files. And note, first of all, that we are pegging it right at about 12 gigabits per second. It starts to break up. Might have been better if we pegged it at 11.5 gigabits per second. But at no time during the transfer did we lose any packets or retransmit anything, as you can see in the graph on the right. So that's just an example of how addressing burstiness in your transmission can help your throughput. Other tuning, Ethernet drivers, Ethernet offloading, Ethernet flow control, which is communication between Ethernet switches and other Ethernet switches or computers to say, wait, I'm full, don't send me more data right now. Storage system configuration, there's a link to the faster data storage system page. And of course, maximum transmission unit. As I said, most of the packets in the world are 1,500 bytes, but you can, if you groom your network path and your machines at the end, you can get as high as 9,000 bytes in typical situations on REN networks. If you experience sickly performance due to queue loss, you might try reducing the max TCP receive window, because if you ask the network for less performance, you'll stop overflowing those queues and you might actually get more done at a lower rate. Parallelism is the way to go. You might find things that say 10 gigabit or 10 gigabit Ethernet can be filled by a typical server grade computer right now. On 100 gigabit, various transfer speeds more than 80 gigabits have been recorded. And the picture calling that 80 gigabit transfer speed a typical transfer speed is like calling the Blue Flame a typical car. Everything was lined up just perfectly. More likely that you'll see 30 gigabit per second flows between 100 gigabit interfaces on a typical day. Most transfers over 10 gigabits per second use multiple connections. Globus grid FTP opens on the order of several hundred connections at once. So I'm aware that I'm kind of running long, but here's a slide about if you're stuck with SSH-based programs like SCP, SFTP, rsync, or other things, there's a way to patch it so it moves better. Sean's gonna talk about grid FTP. This is a results from the patched SSH over the unpatched SSH. So if you're using rsync or SFTP to move files and your throughput is lousy and you can't simply change to Globus or something, it can be patched and you can do a lot better. This is a path between Hawaii and Guam. So that's where the cable between Hawaii and Guam actually lays on the seabed. And so we made these two computers, which are both in